If you've ever seen a mason build a wall, just laying one brick at a time until this huge structure appears, well, that's kind of how our entire universe is built. So what are the bricks? What are the absolute fundamental building blocks of everything you see and touch? That's the journey we're going on right now.
I mean, really think about it. What if you could take anything, your phone, the chair you're sitting on, even the air, and just keep breaking it in half, and in half again, and again? Where would you stop? What's the smallest possible piece of everything?
All right, so here's the game plan for this explainer. First, we'll look at an ancient, indivisible idea, where this all started. Then we'll get into the laws that really govern matter. After that, we'll see how Dalton's atomic theory tied it all together. Then we'll zoom in on the building blocks themselves, and finally, we'll actually learn how to speak the language of chemistry. Let's do it.
So you might think our story starts in some high-tech lab, right? Nope. Our journey actually begins way, way back. Not with scientists, but with philosophers, with thinkers who are just asking these huge questions about what the world is made of.
And what's so cool is that this idea wasn't just in one place. Around 500 BC in India, a philosopher named Maharishi Kanad talked about Parmanu, which he said was the smallest ultimate particle. And get this, around the exact same time over in Greece, Democritus suggested the idea of atoms, a word that literally means uncuttable or indivisible. But for the next 2,000 years, that's all it was, just an incredible idea.
So, how do you make that jump from just an idea to actual hard science? Well, it all started with some really careful, really meticulous experiments by pioneers like Antoine Lavoisier and Joseph Prost. They were the ones who started to lay a real scientific foundation.
Okay, check this out. It's a brilliant experiment that shows the first major breakthrough. You've got a sealed flask, and inside you have two different solutions. Let's call them X and Y, but they're kept separate. First thing you do, you weigh the whole setup. Then you just tilt the flask, let the two solutions mix, and poof, a chemical reaction happens. Maybe you see some bubbles, maybe the color changes. Now for the big question. What happens when you weigh it again?
The mass is exactly the same. Down to the tiniest decimal point, the weight hasn't changed at all. This was huge. It meant matter doesn't just disappear, it just gets rearranged. And that gave us the first great law of chemistry, the law of conservation of mass. You can't create it, you can't destroy it.
So that's law number one. The next piece of the puzzle came from noticing something else that was super consistent. Take water, H2O. It doesn't matter if it's from an iceberg or your kitchen sink. The ratio of the mass of hydrogen to the mass of oxygen is always 1:8, no exceptions. Same thing with ammonia. It's always a 14:3 mass ratio of nitrogen to hydrogen. It's like the universe follows very, very strict recipes.
And Joseph L. Proust summed this up perfectly with what we now call the law of constant proportions. Basically, the recipe for any given compound is fixed. It never changes. So now we've got these two rock-solid laws. But the big, nagging question was still there. Why? Why does this happen?
Why do these laws work every single time? This is where our architect, John Dalton, enters the picture. He's the guy who took that ancient philosophical idea of atoms and brilliantly connected it to these brand new scientific laws.
And Dalton's own story is just amazing. I mean, he wasn't from some wealthy family of scientists. He was born to a poor weaver's family in England, and he became a teacher when he was only 12 years old. Just goes to show you what a curious mind can accomplish.
So here was his brilliant insight. He said, okay, let's just assume that everything is made of these tiny particles called atoms. If that's true, then, well, if atoms can't be created or destroyed, they just get rearranged in a reaction, boom, that explains the law of conservation of mass. And if atoms combine in simple fixed whole number ratios, like 2 hydrogens for every 1 oxygen, well, that perfectly explains the law of constant proportions. All of a sudden, everything just clicked into place.
Okay, so Dalton gave us the blueprint. Now, scientists could finally start to zoom in. What are these atoms actually like? Just how big, or, how mind-bogglingly small are they?
And that led to a massive problem. A huge one, really. If atoms are real, they have to have some kind of mass. But how on earth do you weigh a single invisible particle? It's not like you can just pop one on a kitchen scale.
The solution was just genius. It's all about thinking relatively. If you can't get an absolute weight, you find a standard and compare everything to that. The source material has this fantastic analogy. Imagine a fruit seller who doesn't have any standard weights.
So he just grabs a big watermelon and says, all right, this watermelon is my new standard. I'll call it 12 units. Then he can weigh any other fruit by seeing how it compares to his watermelon.
And that is almost exactly what early chemists did. They picked one specific element, an atom of carbon-12, to be their watermelon. They defined one atomic mass unit, or U, as being exactly 1/12 the mass of that single carbon-12 atom. From there, they could figure out the relative mass of every other atom on the planet. Pretty clever, right?
And we really need a system like this because the scale we're talking about here is, well, it's just insane. A single hydrogen atom has a radius of about 10 to the power of -10 meters. To put that in perspective, you could stack millions and millions and millions of them on top of each other just to match the thickness of a single piece of paper. They're unbelievably tiny.
All right, for our final section, let's shift gears from theory to practice. We've got the laws, we've got the building blocks. Now it's time to actually learn to speak the language, how to write the chemical formulas that describe pretty much every substance in the entire universe.
The secret to this language is a concept called valency, and the source material has this perfect analogy to explain it. Think of valency as an atom's combining power, or even better, think of it as the number of arms an atom has to grab onto other atoms. You know, a human has 2 arms, an octopus has 8. Different atoms have a different number of arms they can use to make bonds.
And this is how we use it. It's so simple. Let's say we want the formula for magnesium chloride. Step 1, you write down the symbols, Mg for magnesium and Cl for chlorine. Step 2, you write their valencies, or their number of arms, right above them. Magnesium has 2, chlorine has 1. Now for the magic trick, step 3, you crisscross those numbers. The 2 from magnesium slides down to become the subscript for chlorine, and the 1 from chlorine slides over to magnesium. So step 4, our final formula is MgCl2. It means one magnesium atom is holding hands with 2 chlorine atoms. That's it.
So, there we go. We've literally gone on a journey from a philosophical dream in ancient Greece and India, all the way to the foundational laws of matter, to Dalton's brilliant theory that explained it all, and finally to the actual language we use to write the recipes for creation itself. We basically have the universe's blueprint. The only question left is, what do we want to build with it?